Our journey begins in ancient times, long before modern technology. Early humans navigated using landmarks like mountains and rivers. The sun and stars provided direction. Polaris, the North Star, was crucial for navigation. The magnetic compass revolutionized navigation. The sextant and chronometer improved accuracy. These advancements ushered in a new era of exploration. Long before compasses and GPS, ancient humans relied on nature to navigate. They observed their surroundings, understanding cues and patterns. Rustling leaves, animal tracks and rivers guided their movements. Landmarks and mental maps were crucial for navigation. Mountains, rock formations and trees served as beacons. These landmarks held cultural and spiritual significance. Day and night cycles, moon phases and seasons tracked time. The sun's movement helped maintain direction. The moon's phases marked time and illuminated paths. Survival depended on understanding the natural world. They predicted weather, found food and water, and navigated terrain. Their knowledge laid the foundation for sophisticated navigation. As humans ventured farther, they turned their gaze upwards to the heavens for guidance. The sun, moon and stars became their constant companions, providing reliable navigational cues. The sun's daily journey marked east and west. At night, stars transformed the sky into a celestial tapestry. Ancient cultures developed intricate systems of star navigation. Polaris, the North Star, remained relatively fixed, guiding navigators. Polaris became a beacon for Northern Hemisphere navigators. By aligning with Polaris, sailors determined their direction north. In the Southern Hemisphere, navigators relied on the Southern Cross. Celestial bodies were deeply intertwined with mythology and religion. Stars were often seen as deities with spiritual significance. Temples were aligned with celestial events, reflecting the connection between heavens and earth. As human societies grew, precise navigation became crucial. Early navigators developed tools and techniques. Simple maps on bone, wood, or clay tablets emerged. These maps depicted coastlines and landmarks. They aided in memorizing routes. Maps grew sophisticated, showing direction and distance. Instruments like the gnomon measured the sun's altitude. The astrolabe measured celestial altitudes precisely. These tools enabled confident navigation. Ancient civilizations relied on celestial navigation. The magnetic compass, developed in ancient China, revolutionized seafaring. It harnessed Earth's magnetic field, providing reliable direction. Early compasses were simple lodestones. These aligned with magnetic north. This freed sailors from celestial navigation. They could navigate confidently even at night. The compass enabled accurate course maintenance. It reduced the risk of getting lost. Portolan charts depicted coastlines and harbors. The compass spread along the Silk Road. It reached Europe in the 12th century, sparking the age of exploration. Explorers sought new trade routes and discovered new lands. The age of exploration, spanning the 15th to 17th centuries, was a transformative period driven by curiosity, ambition, and technological innovation. European powers financed daring voyages to establish new trade routes and expand their empires. Navigators, armed with the compass and astrolabe, charted new sea routes and encountered new cultures. Portuguese explorers, led by Prince Henry the Navigator, spearheaded early voyages of discovery. They explored the west coast of Africa, establishing trading posts and searching for a sea route to India. Bartolomeu Dias rounded the Cape of Good Hope in 1488, proving it was possible to sail around Africa to reach the Indian Ocean. Vasco da Gama's voyage to India in 1498 opened a direct sea route to the east. Christopher Columbus's voyage in 1492 led to the European discovery of the Americas. Columbus's voyages sparked an era of colonization, cultural exchange, and the transatlantic slave trade. Other explorers, including Amerigo Vespucci, Ferdinand Magellan, and Sir Francis Drake, expanded European knowledge of the globe. The age of exploration was not without its dark side. European exploration often led to the exploitation and subjugation of indigenous peoples and the introduction of diseases that devastated native populations. However, it also marked a turning point in human history, expanding our understanding of the world and connecting distant cultures through trade, diplomacy, and the exchange of ideas. The sextant precision at sea and the quest for longitude. While the compass provided direction, determining exact position, especially longitude, was challenging. Latitude was easier to determine by measuring the sun or Polaris. Longitude, however, was elusive. The sextant's invention in the 18th century revolutionized navigation. It measured angles with unprecedented accuracy. This precision was crucial for safe navigation. Measuring the sun or Polaris allowed precise latitude calculation. This was vital for approaching land safely. Longitude required precise time measurement. Accurate clocks were essential for determining longitude. Each hour of time difference equals 15 degrees of longitude. Navigators needed precise clocks for accurate longitude. The longitude problem, a nautical conundrum. For centuries, the vast expanse of the ocean presented a formidable challenge to navigators, the elusive mystery of longitude. Determining latitude was straightforward using celestial navigation, but pinpointing longitude remained a perplexing puzzle. The inability to accurately determine longitude at sea led to navigational errors and shipwrecks. The crux of the longitude problem lay in the relationship between time and longitude. Navigators needed a reliable method of measuring time at sea, but traditional pendulum clocks were inaccurate due to the conditions at sea. John Harrison, A Clockmaker's Quest for Accuracy. In the early 18th century, John Harrison, a self-taught clockmaker, dedicated his life to creating a timepiece that could withstand sea travel. Harrison's approach was radical. He recognized the limitations of pendulum clocks at sea. He embarked on a quest to design a clock impervious to the ship's motion and temperature variations. After decades of experimentation, Harrison unveiled the H4 in 1759. A revolutionary timepiece resembling a large pocket watch. The H4 incorporated ingenious inventions including a bimetallic strip and a novel escapement mechanism. Section 3, H4 and the Triumph of Time, Revolutionizing Navigation. The H4 marked a turning point in navigation, providing mariners with a reliable means of determining longitude. To prove its accuracy, Harrison's son, William, embarked on a transatlantic voyage in 1761. The H4 lost only 5 seconds during the journey, surpassing the standards set by the Board of Longitude. The H4's success led to the mass production of marine chronometers, revolutionizing maritime navigation. Accurate longitude determination enabled the creation of detailed nautical charts, facilitating global trade and exploration. The rise of radio navigation, finding direction through the airwaves. The invention of the radio opened up new possibilities for communication and navigation. Radio direction finders, RDFs, allowed ships and aircraft to determine their direction relative to a known radio transmitter. RDFs were valuable in maritime navigation, providing a reliable means of determining position in fog or storms. Coastal radio beacons emitted signals that could be picked up by RDFs, allowing ships to navigate safely. The use of radio navigation expanded rapidly, improving accuracy and range for both military and civilian navigation. Radar, seeing through the dark and fog of war. World War II spurred technological innovation, including radar, which revolutionized warfare and navigation. Radar systems transmit pulses of radio waves and detect echoes to calculate the distance and bearing of objects. Radar played a pivotal role in air and naval warfare, enabling the detection of enemy aircraft and ships. Beyond military applications, radar proved valuable for navigation in aviation and maritime transport. Radar allowed aircraft and ships to navigate through clouds, storms, and darkness, improving safety and efficiency. The rapid growth of aviation brought new challenges to navigation. Pilots needed reliable navigational aids for accurate guidance in challenging weather conditions. VOR, Very High Frequency Omnidirectional Range, and NDB, Non-Directional Beacon, emerged as cornerstones of air traffic control. VOR stations transmit a rotating signal, allowing aircraft to determine their bearing relative to the station. NDBs transmit a non-directional signal, allowing aircraft to determine their bearing using a radio direction finder. These systems made air travel safer and more efficient, enabling the growth of commercial aviation. The year 1957 marked a pivotal moment with the launch of Sputnik, the world's first artificial satellite. Sputnik's significance extended beyond the space race. It revolutionized navigation. By tracking the satellite's position and analyzing the Doppler shift of its signals, accurate location determination became possible. Sputnik's launch sparked research into satellite-based navigation systems. The US developed the Transit System, the first satellite-based navigation system for the Navy. These early systems laid the groundwork for the Global Positioning System, GPS. The Cold War led to the development of the Global Positioning System, GPS. GPS relied on a constellation of satellites transmitting precise time signals and orbital parameters. By receiving signals from multiple satellites, GPS receivers could calculate their position with remarkable accuracy. The system became fully operational in the early 1990s, providing global coverage. The Gulf War demonstrated GPS's capabilities in navigation and troop coordination. The US government made GPS accessible to civilian users, transforming navigation and unleashing innovation. The widespread availability of GPS in the 1990s marked a watershed moment in the history of navigation. What began as a Cold War military technology rapidly evolved into an indispensable tool for countless civilian applications, transforming industries, fostering innovation, and fundamentally changing the way we live, work, and explore our world. The aviation industry was among the first to embrace GPS technology. Aircraft equipped with GPS receivers could navigate with greater precision, follow more direct routes, and land in challenging weather conditions with increased safety. GPS revolutionized air traffic control, enabling more efficient use of airspace, reducing flight times, and improving fuel efficiency. The maritime industry also benefited greatly from the advent of GPS. Ships, from massive cargo vessels to small fishing boats, could navigate with greater accuracy, track their positions in real time, and improve safety at sea. GPS-enabled navigation systems became essential tools for search and rescue operations, enabling rescuers to locate and assist vessels in distress with greater speed and efficiency. Beyond its impact on aviation and maritime transport, GPS rapidly permeated countless other industries and aspects of modern life. Surveying and mapping were revolutionized by the accuracy and efficiency of GPS-based surveying equipment. Farmers used GPS-guided tractors for precision agriculture, optimizing crop yields and reducing the use of fertilizers and pesticides. Geologists and environmental scientists used GPS to track earthquakes, monitor volcanic activity, and study the effects of climate change. Beyond GPS, the emergence of global navigation satellite systems, GNSS. While GPS revolutionized navigation and became a global utility, it wasn't long before other nations recognized the strategic and economic importance of having their own satellite navigation systems. The early 21st century witnessed the rise of multiple independent global navigation satellite systems, each with its own constellation of satellites and unique capabilities, further enhancing global navigation and positioning. Russia developed its own system, GLONASS, initially for military purposes but later made available for civilian use. GLONASS, with its constellation of satellites in a slightly different orbital configuration than GPS, offered an alternative navigation solution, particularly in high-latitude regions where GPS signals could be obstructed. Europe, seeking technological independence and aiming to provide its citizens and businesses with a reliable navigation solution, developed Galileo, a GNSS with a strong focus on civilian applications. Galileo boasts advanced signal structure and enhanced accuracy, particularly in urban environments where tall buildings can interfere with satellite signals. China, a rising global power, established its own GNSS, Beidou, meaning Big Dipper, with ambitions to provide global coverage and compete with GPS in terms of accuracy and reliability. Beidou's development reflects China's growing technological prowess and its desire to assert its presence on the global stage. A constellation of benefits: accuracy, resilience, and global coverage. The emergence of multiple GNSS constellations has ushered in a new era of navigation, offering a plethora of benefits for users worldwide. The availability of signals from multiple systems enhances positioning accuracy, particularly in challenging environments such as urban canyons or mountainous terrain where signals from one system might be obstructed. The redundancy provided by multiple GNSS constellations also enhances the resilience of navigation systems. If one system experiences technical difficulties or signal outages, users can still rely on signals from other systems, ensuring continuity of service and reducing the risk of disruptions to critical infrastructure and applications. Global coverage is another significant advantage of multi-constellation GNSS, with different systems having varying satellite distribution and orbital characteristics. Users in remote areas or at high latitudes can benefit from improved signal availability and positioning accuracy, expanding the reach of precise navigation to nearly every corner of the globe. The availability of multiple GNSS constellations has spurred innovation in receiver technology. Modern GNSS receivers are designed to simultaneously track and process signals from multiple systems, leveraging the strengths of each system to provide optimal positioning accuracy, reliability, and availability. This multi-constellation capability has become the standard for high-precision applications such as surveying, geodesy, and scientific research. Navigation's enduring legacy, shaping our world, connecting our lives. From the earliest humans who looked to the stars for guidance to the sophisticated satellite networks that guide us today, navigation has shaped human history, driven exploration, and transformed how we live and interact with the world. From rudimentary tools to GPS, navigation connects continents and cultures. It enables global trade, cultural exchange, and scientific collaboration. Navigation systems are indispensable in our daily lives. They remind us of our enduring quest to find our way. Charting the future of finding our way. Innovation on the horizon. The evolution of navigation technology is remarkable, and the journey continues. Future navigation expands with AI, sensors, and data analytics. Emerging technologies promise enhanced navigation accuracy and reliability. Self-driving cars, guided by sensors, are becoming a reality. AI enables precise navigation, promising to revolutionize transportation. Indoor positioning systems extend precise navigation indoors. Technologies like Bluetooth beacons enable accurate indoor navigation. Quantum navigation holds revolutionary potential. Quantum sensors offer unprecedented accuracy, paving the way for ultra-precise navigation. Hit that like button, subscribe, and stay informed.